Hey guys, this is Carrie, and this is lesson 1 from Unit 9. And so this is actually a non-programming lesson, and we're going to start off by talking about how computers work. We probably won't be programming in this unit. This unit is actually going to be all about getting a deeper understanding of the technological devices that we use on a daily basis. All right, so first off, we're going to introduce some terminology. What is a computational device? And so when we think about a computer, you probably think about like a desktop computer or a laptop. But actually, we use a lot of other computational devices on a daily basis. So we use things like iPads, which I'm writing on right now. We use things like smartphones, laptops, and all of these things are computational devices. The most important thing to think about when you're thinking about computational devices is that computational devices take inputs, they process them, and that leads to outputs. So if you think about working on your computer or working on your phone, it takes in a variety of different inputs. Like right now, it's taking in my screenwriting. It's taking in my audio. If you type on a keyboard, we have that. The mouse would be an input. There are tons of ways that you can input data into your computer. The internet, right? When you download a file, you're inputting new data into your computer. So computational devices all start with inputs. Then something's done to process them. So at the end of this video, right, what's going to happen is it's going to convert this audio and video to, I think it's an MP4 file. And then finally, it's going to output something, which is the MP4 file in this case. However, if we connect this back to our programming, we used to write things in HTML, CSS, and JavaScript. And that would be an input, the program code that we wrote. The processing them would be in the web browser. When we double-click them, something would happen, right? Magically, it would read through all that code. And then the output would be a web page. And so computational devices, these are the 3 criterion that something needs to have in order to be a computational device. At the end of this unit, or the next unit, I'm not sure exactly where we're going to break things. It depends on the timing. You're going to be researching a computational device of your own choice, so you can start thinking about that now. Are you interested in researching your smartphone? Maybe virtual reality goggles. Maybe a brand new camera that does something special when you take pictures. It's really going to be your choice, but you can start thinking about that now. All right, so when you think about a computer, it kind of feels like the computer works magically. And we're going to talk today about some of the basic key components about how a computer works. So I think the most important image that you have in your mind when you think about a computer, right, is you've got that basic image of a computer. Maybe you have the screen, maybe you've got the keyboard, maybe you've got a trackpad here. But actually, what we're going to be looking at today is what happens on a deeper level inside of the computer. So if you're thinking about a laptop, it would be what's happening kind of in here, or in your smartphone, what's happening behind the screen, what happens inside. And because humans built computers, the best way to understand how computers actually work is to think about how your mind works. So the components inside of a computer often have analogous models inside of the human mind. And I think that that's a useful tool to think about. So if you think about what does your mind do, your mind remembers things. A computer needs the ability to remember stuff. When you save a file to it, it's got to be able to remember it. Your computer needs to have the ability to process things. And so does your brain, right? You can process different things. You can try to problem solve. Do calculations. Think. Your computer needs to have the ability to do those things as well. So what part of the computer does that? And then also your computer has to have the ability to work on current things. And that's a little different from remembering things, right? If you think about your own memory, you've got this long-term memory. Like, you probably remember your parents' cell phone number, but you weren't currently thinking about it. You have like a long list of things that maybe you're currently thinking about. Probably only part of that is computer science right now, and then other parts would be, I don't know, COVID-19, or an email that you just got, or your English essay that you have to write. And that's something that you want to think about when you're thinking about current things. There are a lot of other things that a computer does, right? It takes in input, but that's pretty self-explanatory. So you've got like the keyboard, you've got the trackpad, you've got the microphone or the camera here. So we're not going to focus too much on that. All right, so trying to figure out what each of the different parts are used for. The computer has a really important component called the CPU, the Central Processing Unit. And the Central Processing Unit is where all of the actual thinking, all of the processing happens here. And the way that you can tell you have a really good processor is it can do a lot of thoughts every second, or a lot of calculations every second. So if you think about the analog of your brain, this isn't something long-term in your memory or anything like that. This is like you actively trying to solve a problem, you actively doing calculations. I don't know, maybe a good image to have would be if you were in elementary school and your teacher asked you to do as many math problems as possible in the next 5 minutes, your CPU, like your brain CPU, would be overworked because it would be trying to do as many calculations as possible in that second. So it's good to have that picture in mind as you think about the CPU. But doing all these calculations would kind of be irrelevant, right? Unless we could actually remember what we were doing. So your computer has two different types of memory, as we hinted at before. One of these is called hard drive memory. And hard drive memory is long-term memory. And if you think about stuff, a lot of the time, you might, I don't know, maybe you'd hear something, like maybe I'll hear this lesson, and that will be in your short-term memory, and that's what RAM is. But it's very possible that at the end of this lesson, even if you think about everything while you're doing this lesson, even if all of this is in your short-term memory, you may have a hard time saving it to your long-term memory inside of your brain. The same way that we have that distinction, short-term memory, things that we're currently thinking about, computers also have that same distinction, things that they're currently thinking about, files that are currently open, versus things that are stored long-term in the computer. So for long-term memory, what you want to think about is files that are not currently open. So you might have a set of audio files from your favorite musician, a set of pictures that you took in your computer, and those are always there in the memory. They're permanently there in the memory. But they're not actively being thought about right now. And this is relevant when you think about the human brain too. You probably have things that are in your long-term memory, like how to tie a shoe, which is not something that you're currently thinking about, but is permanently there in your mind. All right, so now when you double-click on something that's in the long-term memory, it loads it from the long-term memory into the short-term memory. And that's what RAM is used for. So these are short-term memory. And the good analogy for RAM is it's like what you're currently thinking about or what you're currently working on. And there's a little bit of a distinction here, and I think it's relevant, again, kind of to keep connecting it back to the human brain, which is it's hard to keep track of a lot of things in your short-term memory. It's hard to have a lot of things open. The same way that your the same is true for your computer. It's very taxing to have a lot of things going on in the working memory. And you can see this with computers. A lot of computers will have something like 2 gigabytes of working memory. meaning that they could think about 2 gigabytes, and we'll talk more about what a byte is in a later lesson, 2 gigabytes worth of information that they're currently thinking about. Long-term memory, on the other hand, similar to the human mind, it's like you can store a lot more stuff in your long-term memory. So with long-term memory, you might see something like 2,000 gigabytes worth of space. And the reason why these things are different is it turns out that the tools used to store this information, the actual hardware inside of your computer, you can tell from the appearance, actually looks pretty different. So RAM has to be very fast because you're currently working on it, whereas a hard drive can be a little slower because it's just stuff that is stored and then you double click it to open it. Maybe it takes a little while to load it up. And because it can be slower, it doesn't have to be as... it's not as expensive, basically, as RAM. All right, so basically we've got our model of the computer as a human brain. We can store things long-term in the memory. We can work on stuff. We can take things from the long-term memory and load it up into our short-term memory so we're currently thinking about it. But then where all of the work happens, where all the calculations, where all of the commands like saving or opening things happens, that's the central processing unit. And these together make up a really functional piece of software. You can type in inputs, they go into the CPU. The CPU maybe changes something in the working memory, like the words in a file or the color of a website. You save it back. Now it's on the hard drive. You close your computer. All of the RAM disappears when you close your computer. You reopen it. And then when you double click that icon, it loads it from the hard drive back into the RAM. And you have this really dynamic understanding of what's happening inside of the computer. All right, so continuing on. We might wonder in more detail, how is any of this stuff actually happening? What does memory actually look like inside of a computer? What does RAM look like? What is the CPU even? And computers work in a pretty interesting way. Computers use something called bits to represent all data. And then you might wonder, what is a bit? And so if I were thinking about a computer, let's say I wanted to type the number 10 or like the number 7 into a computer. If I was trying to think about what happened when I typed 7 into the computer, maybe like I would imagine that, I don't know, like 7 volts or something of electric potential goes into a wire. And the computer can tell that it's like 7 volts because it's got like, it can accurately read that. It turns out none of that is true. When a computer thinks about things, it turns out that having exactly 7 volts would be really difficult. You'd have to have like something to set the 7 volts, something to read it. It would be really hard to tell, is it 7? Is it 7.2? Is it 8? Is it 6? And as your computer grew older over time, you could imagine that it would be harder to maintain this exact value. So rather than do stuff like that, your computer actually uses a completely different idea. Your computer is basically a set of on and off switches. And the reason why this is important is it's really easy to tell if a wire is on, if there's current going through it. It doesn't matter how much current. If it's on, it will read as on. And if it's off, it will read as off. So we don't have the same performance degradation over time, and we also don't have the same issues with sensitivity about reading exact values. It's either on or off. And so the smallest unit of memory inside of your computer is basically something that is either on or off. So on a hard drive, it might be a magnet facing up or down. So plus minus versus minus plus. This would be on, this would be off. Maybe it's current in a wire or current in a wire. And there's either current going through the wire or no current at all going through the wire, and it's a broken connection. And that would be on or off. And the common symbol when we think about things being on or off is to think about them as a 1 or a 0. So when something is on, we say the value is 1, and when it's off, the value is 0. Now this is really interesting. This is the fundamental thing that computers are built out of, these on-off switches. So if you think about some data types, like if I were to ask you a yes or no series of questions, like, I don't know, are you passing computer science? You could say 1, which would mean maybe, yes, I'm definitely passing computer science. And the computer could put current through the wire to say that. Or you could say 0, which might mean no. And because there are two states, either yes or no, it'd be very easy for you to answer that question. So some other things that are really easy to answer are maybe like a mouse, right? When you click it, it's a 1 because the mouse was clicked. And when you're not clicking, it's a 0. It's off. The click is off. When a button is pressed on the keyboard, 1 because the button is down, 0 because the button is off. When I'm recording this, it will be 1 that I'm recording because it's on the recorder, and then when I stop recording, it will be off. And so there are certain things that are really easy to connect to two states, on and off. But then there are other things that are really hard to imagine. Like, how does your computer store the number 3, or let's talk about numbers. How does your computer store something like a movie? Right? Like if you think about a movie, it's not really like on or off. Like, I mean, right, you can turn a movie on or off, but the actual data that makes up the movie is really complex. It's all of those pixels, it's all of that audio. But somehow, even a movie or a Word document or a song, all of that stuff is stored in your computer as collections of ones and zeros. And what we're going to be talking about in this unit is to get a deeper understanding of how do you take a complex data type like a movie and teach your computer how to store that as a collection of ones and zeros. All right, so I think this is a good opportunity for you to take a moment and test your understanding. So can you try to explain why Boolean values are easy to represent using bits? And whenever I say bits, I want you to think 1 or 0. Current going through the wire or no current going through the wire. Why would a Boolean value be easy to represent using this? So when I check your work, I'll be checking that you have all of the notes complete, but also the checkpoint complete. For the next one, numbers are a little more challenging to represent with bits. Like certain numbers like 1 or 0 seem easy, but why might a number like, I don't know, 1,756 views on YouTube, why might that be challenging? Or why might it be challenging to say that, to store like the number 3.1415 ... Why would it be challenging to store pi in a computer? The important thing to keep in mind after you're done answering these two questions is even though some things are easy, like Boolean values, and some things are complex, on a fundamental level, everything in a computer is stored as either a 1 or a 0. All right, so I'm not going to review the two checkpoints. That's going to be for you to test your understanding, and then I'll review it when you send me your answers. But connecting this back to numbers, we're going to try to figure out how movies are stored, how colors are stored, how words are stored. It seems like numbers might be a good starting point. So let's think about how to count with bits. So if you just had one bit, well, you could say when it's off, that would be, we'd store that as 0, and when it's on, we would store that as 1. So you can think about this like a little light bulb inside of your computer, that if the light bulb is on, now that's the number 1. But if you just had one bit of memory in your computer, it's either going to be off or on, 0 or 1. There's no way to represent the number 2. So in order to represent the number 2, what we can say is, well, let's put 2 bits of information on our computer. And maybe we'll put them side by side. So if they're both off, and I'm going to start using 0 for off, maybe 0, 0 would still be 0. The next one higher would be, okay, well, we know that we can change it to 0, 1, and that would be the number 1. Now, we can't change this one to a 2 because it's either off or on. So if we want to represent 2, we'd have to say, okay, well, we've totally done everything we can with this first bit. So let's move over to the next bit. Let's make this one a 1 and this one a 0. And that would be 2. And then if we want to make another number, well, we've done 0, 0, 0, 1, 1, 0. The largest number that we can make is turning both switches on, and that would be the number 3. So with 2 bits, we can now, using only zeros and ones, represent the numbers 0, 1, 2, and 3. With 3 bits, let's see what happens. So we might say, okay, well, 0, 0, 0 would be 0. 0, 0, 1 would be 1. We want to make 2, but we don't have the ability to put a 2 in that spot because it's either off or on. So instead we have to say, okay, well, we'll do 0, 1, 0 for 2. And then here we had 1, 1. So 0, 1, 1 would be 3. Now there's no other combination that we can make with just these 2 bits. So if we want to make the next biggest number, maybe we should put a 1 here and then 0 in the 2 other spots, and that would be 4. And then 1, 0, 1 could be 5. 1, 1, 0 could be 6. 1, 1, 1 could be 7. And it looks like we're able to represent more numbers. We're going to talk in more detail about how we actually convert these numbers to normal numbers in 1 second. But what's important to understand is as we put more and more bits here, we can actually represent larger and larger normal numbers using different combinations of 0 and 1. Okay, so let's get into a more detailed understanding of why exactly is this 111 actually equal to 7 in your computer's memory. In order to understand that, you need to understand a little bit more about the decimal number system. We take for granted things like 397. This number is called a decimal number, even though it's not actually a decimal. And when we say decimal in this context, what we mean is deci. That means 10, like decagon, or similar to diez in Spanish, or dieci in Italian, like deca, deci, that all comes from, decade, that all means 10. And so the reason why we call this decimal, this number, it's a very familiar number, 397, is if you think about each of the spots, this didn't have to be a 7. It could have been a 0, a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, or a 9. We have 10 possible symbols. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible symbols that could have gone in this spot. And so because we have 10 possible symbols to go in that spot, we call it base 10, or decimal. And the best way to understand base 10 or decimal is to think back to, I don't know, elementary school, when you had little blocks and cubes that you were playing with. So you might have thought about the number 397 as, okay, I've got 7 of these, and I'm going to regret picking 7. I've got 7 of these little ones cubes. And you probably had a teacher that made you play around with those little cubes. So you had 7 of these little ones cubes. Let me write that a little neater. Let me just write this times 7. So you got 7 ones. But then when you had 10 ones, right, something interesting happened. Those 10 little ones cubes joined together to make a tens rod. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that tens rod counted as 10 cubes because it was 10 cubes long. And the analog here is, well, we had 7 of these ones. For the number 397, we would have 9 of these tens rods. And this would be called the tens place, right? If you think about math classes rounding. And then when you got to 10 rods, you no longer kept adding rods because you run out of symbols to put here. This would become the hundreds place. And that would be like a big block of 100 things. And you probably remember that from elementary school. I'm not sure if that's exactly 10. And this number would be 397 cubes would be 3 of these hundreds, 9 of these rods, and 7 of these little ones places. Well, there's an interesting pattern here. If you think about place value here, to go from ones place to tens place, tens place to hundreds place, that's times 10. Because 1 times 10 is 10, 10 times 10 is 100. The next one, if we had it, would be the thousands place, 10,000s place. It's always times 10 to get the place values. So you're going to hear me using the word place value quite a bit. So in binary, things work really similarly. In binary, and the reason why we call it binary is the prefix bi means two options. So here, this would either be a 0 or a 1. So deci was the case because we had 10 options for this number. In binary, you're going to have two options for each number, for each digit. And they're going to be either a 0 or a 1. So if we think about a binary number, like, I don't know, 10110, it's a number that consists only of two different options, 0 or 1 for each digit. Now, the same way that we did before, we have to think about place value. So you always start with the ones place. But this time, instead of multiplying by 10, like we did with decimal, this will be the twos place. So that will tell us how many twos we have. And then times 2 again, this will be, okay, and it's starting to get a little hard with all the s's, so I'm going to write this in a better way. This will be the ones place, this will be the twos place, times 2 would make this the fours place, this would be times 2 would make this the eights place, and this times 2 would make this the 16s place. So this binary number says to us, okay, we've got 0 ones, we've got 1 2, we've got 1 4, we've got no 8s, we've got 1 16. So we count only the ones that we have a 1 in because we have one of each of those numbers. So we have 2 plus 4 plus 16. This would actually be 10110, the number 22. So to help you out getting some experience with this weird number system, let's move on to checkpoint 3. So you're going to be doing most of these on your own, but I think it will be helpful to have a couple of examples. So let's do the first one in each column together. So we're starting off with a binary number. How your computer might store a number, all ones and zeros, and you're going to be converting that to a decimal number. So if we put our place values here, we've got, I'll do the first one here, okay? So we've got in the ones place a 1. Now the place values, it's times 2, right? So this would be the twos place. This would be the fours place. This would be the eights place. Times 2 would be the 16s place. So we've got 0 16s, 0 8s, 0 4s, 0 2s, just 1 1. So this is actually just the number 1 in disguise. Looking at a more complex number, like this binary number here, in column 2, we could put same place values, the ones place, times 2, twos place, fours place, eights place, 16s place, 32s place, 32 times 2 is 64. So that would be, okay, we've got 164, we've got 1 2, and we've got 1 1. So that would be the number 67 in disguise. And it's amazing, using only ones and zeros, your computer now has a way to store the number 67. So I think it's a good moment now to pause and to try this on your own. And I'll review one more of these after you try it on your own. So you can watch that to check your work afterwards. Okay, so I think the one that might be fun to review, maybe this one right here, because it looks like the most complicated. So in our ones place, we've got 1 1. This is the twos place. We have 0 2s. We've got 0 4s. We've got 0 8s. We've got 1 16. We've got 1 32. And we have 0 64s. All right, so putting that all together, we've got 132. So we'll write 32 here. We've got 116. And we've got 1 1. So if we add those all up, we get 49. So your computer now has a way, right here actually, of storing the number 49 inside of its memory. So if you want to say I'm 49 years old, or this video's gotten 49 views, or it's 49 seconds long, this is how your computer could store that information inside of its actual mind. And the reason why it has to use zeros and ones, right, is these aren't actually zeros and ones. These are current going through wires or not going through the wires. So your computer might think about this as like a series of pulses, off, on, off, on. And that would mean the number 49 to your computer. So hopefully you're getting a feeling for how your computer thinks about things, all zeros and ones, and what the decimal equivalents of those are. So something really interesting happens to me when you count to 24 using binary, using 5 bits for each number. So if we want to write the number 1 in decimal, well, that would be 0001. Why do we use 5 symbols here? Well, they said it had 5 bits of memory, and each one of these slots is either off or on. Each one is a bit. So now if we want to do the number 2, that would be 0010, because we have, okay, that was, I just kind of jumped to that because I know the answer, but where did that answer come from? Well, let's undo that then, and let's think about our place values. So we've got a 1's place, we've got a 2's place, we've got a 4's place, we've got an 8's place, and we've got a 16's place. And if we want to make the number 2, we don't need any 16s. We don't need any 8s. We don't need any 4s. You might say, okay, I need 2 1s, but we're not allowed to have 2 of anything, right? It's either off or on. So we don't need any 1s. What we do need, though, is we need 1, 2, and 0 1s. So in binary, this is how the number 2 looks. Let's do the same thing for the number 3. I'm going to write with a thinner stylus, so hopefully that makes it more readable. So we've got our 1's place, 2's place, 4's place, 8's place, and 16's place. That's 1, 2, 3, 4, 5 spaces, 5 bits. So to make the number 3, you need 0 16s, 0 8s, 0 4s, 1 2, and 1 1. A good analogy here is it's almost like you're making change at a cash register and you're trying to figure out how many $2 bills, $1 bills do I need in order to make change. So the number 3 in binary is actually just written 00011. And as you complete this, you may find that there's a nice pattern for counting in binary, and that would be nice to see and make the problem set easier. But I think maybe you'll discover that as you do this. So please complete the rest of this for your checkpoint 4. In order to help you out with your final answer here, when you're done, you can check to see for 24, if we do that one, 16's place, 8's place, 4's place, 2's place, and 1's place. We've got, to make 24, we need 1 16. Okay, so 24 minus 16, that leaves us with 8. We need 1 8, and that takes care of the 8. And so then we have 0 4s, 0 2s, and 0 1s. So if we have 1 16 and 1 8, yeah, that's 24. Okay, so in binary, the number 24 is 1100. Or your computer might think about it as a flashing current, on, off, off. Perhaps that reminds you a little bit of Morse code, where you use dots and dashes to communicate complex numbers and letters. And that's a good analogy to think about when you think about computer science. So convert the number 40 from decimal to binary. So they're telling you that this is a decimal number. Well, with 40, it's a little bit tricky because they don't tell you how many bits to use. So we can build up our place values from right to left. So for place values, we might think, okay, well, we're going to start with the 1's place, just like we always do. 2's place, we might have 2's. We might have a 4, because 4 is less than 40. We might need an 8. We might need a 16. We might need a 32, because 32 is less than 40. But we definitely don't need any 64s or higher, because 64 is already too large, so we can't have one of these. So when we try to write the number 40 in binary, we don't have to go past the 32's place, because 64 is already too large. Now to make 40, it's easiest to go from left to right. We'll need 132. So 40 minus 32, that leaves us with 8 left. We don't need any 16s because it's already too big to make that 8. We can take 1 8. That leaves us with nothing left. So then 0 4s, 0 2s, and 0 1s. So the number 40 in decimal becomes the number 101000 in binary. And that's how your computer might actually store this number inside of its hard drive. All right, so try the next one on your own. For this one, I think it's really interesting. We start to get into this idea of, in the image below, each row of the image is encoded in an 8-bit binary number. Using zeros as black squares and ones as white squares, shade the pixels to create the encoded image. So this is actually super interesting to me because it starts to highlight how you might store an image inside of your computer's memory. And a black and white image, you could think about, okay, well, your computer screen is a bunch of pixels. Those are the tiny squares on your screen, right? And for each pixel, if it's either going to be black or white, you could say it's either off or on. So that pixel is either going to be off or on. And so we like to think about zeros is off, which would mean that that light is lit up black, and ones is white squares, which would mean that light is turned on because one we think of as on. All right, so the first row would be on, off, I'm going to use this highlighter, on, off, off, on, off, off, on. I don't want to put that there. All right, cool. Whoop. All right, cool. So the next one would be on, off, on. Sorry, on. It's hard to mark them. I'm trying to show you where I'm thinking. Okay, and then the only other one that would be off would be here. All right, so please finish this one up, and you can see how pictures get encoded, or black and white pictures. In a future lesson, we'll talk about colors. So there is some neat stuff if you want some extra practice converting binary stuff. And if you felt like my presentation wasn't clear, this is something that's really commonly taught online, so you'll definitely be able to find another teacher teaching the exact same material. So I definitely recommend giving that a Google and seeing if you can find a teacher whose style you can follow, maybe even a little better if you found this to be a difficult presentation of the material. The last thing to talk about, though, before continuing on with the neat stuff for you guys is, if you think about turning your computer off or on, what's the symbol on that button on your computer? Well, on my Mac, it looks like this. And the reason, sorry, this is totally unrelated to this problem. The reason why this symbol looks like this is it's either a 1 or a 0. So if you combine those two things together, you get this symbol, a 0 with a 1 inside of it. And so turning your computer from off to on changes it from a 0 to a 1. And that's why the on-off switch looks the way it does. So in this lesson, I hope you guys got a basic feel for some of the key components inside of the computer's hardware. And also, start to understand that your computer represents all information as a sequence of ones and zeros. And that can be really challenging with certain things like numbers. But maybe now, after you've learned a little bit of binary, you can see how a number like 17 could actually just be represented as 10001. I think that's right. And that's actually what this number looks like inside of your computer's mind. All right, guys, we'll have a new lesson next time our class meets. Please make sure that you take a picture of your work and you send it to me so I can give you credit for today's lesson. Please also include any questions that you have. And also start thinking about the computational device that you'd like to research. It can be anything that you're interested in. So I don't know if you're interested in like artificial reality or virtual reality or smartwatches or phones, and start thinking about, how does this connect? What inputs does that computer take? Where's that computer's hard drive? Where's that computer's working memory? And it might be a good thing to do.